Let's start with the airframe. Thousands of specially formed, damage-resistant panels are riveted or otherwise attached to a lightweight underlying base called the airframe. The panels and frame together make a very strong, relatively lightweight craft. Many of these parts, especially the outer panels, are made from a carbon fiber reinforced material, though traditional aluminum and aluminum alloys are also used. Vertical frames underpin the cross-sectional tube shape, connected by longerons that stretch from nose to tail. And in between these, a vast network of stringers, intercostals, and subframes. At the nose, the radome shields a weather radar antenna beneath, while allowing specific radio frequencies to pass through for proper functioning. A double-layered bird strike barrier is situated behind that. Floor beams attach to frames and support the floor panels. Higher grade panels are used in high traffic areas and the cockpit or flight deck, with lower grade panels beneath passenger seating areas. Pressure bulkheads are reinforced metal barriers that separate pressurized from non-pressurized areas of the plane. Humans are accustomed to about 14 psi of air pressure. Passenger planes generally fly between 31 and 38,000 feet above sea level, where air pressure is a meager 4 psi or lower. As such, most sections of the airplane are pressurized while in flight. These areas include the flight deck and passenger areas, equipment bays, and cargo compartments. Unpressurized areas are the radome, landing gear bays, the center wing box, and the tail cone. The wings attach near the center of the aircraft. A center wing box ties wing frames together with the fuselage. The keel beam offers additional support. A wing-to-body fairing attaches to the keel beam and a pair of external longerons to enclose and further strengthen this critical wing attach point. Sturdy yet flexible spars stretch from the center wing box to the wing tip, one at the leading edge and one at the trailing edge of the wing. A pylon juts out from the wing frame to support the jet engine. Titanium links extend from the wing to the pylon, and tension bolts mate aluminum and titanium plates for an incredibly strong and flexible connection. Moving to the rear or aft of the plane, we see the vertical and horizontal stabilizers with their additional frame supports, and the tail cone, which houses the auxiliary power unit, or APU. Windows. The windshields and side windows are made from 3 layers of chemically strengthened glass, covered with an anti-static coating. Cabin windows maintain the structural integrity of the fuselage with a thick outer pane made from acrylic. There's an additional protective acrylic pane on the passenger side with a hole and an air gap for pressure and temperature equalization. Doors. There are passenger doors front and rear, with corresponding service doors on the starboard side. Cargo access doors are also on the starboard underside. Smaller overwing emergency doors are located just above each wing. Doors must be disarmed before opening so the emergency slide will not deploy. An overpressure light, visible from the inside and outside the door, indicates whether the pressure differential would permit safe opening. A vent panel enables pressure equalization. Turning the interior latch handle allows the door to be opened. There's also an externally accessible door latch. The door rides on a hinge arm to swing out and away from the plane body, with stabilizer bars to guide its path. Wings and flight control surfaces. The wings generate lift for the aircraft. The main surfaces for flight control are the ailerons, elevators, and rudder. The ailerons generally function opposite one another to roll the plane. Elevators affect forward to back pitch, and the rudder controls yaw, or rotation around the vertical axis. The entire horizontal stabilizer, which the elevators are attached to, can be rotated to hold the plane at a particular attitude and leave the elevators for finer adjustments. To achieve this, the stabilizer is attached to a motorized device that can move up or down a threaded rod. Secondary flight control surfaces assist these primary systems. On the wing, leading edge slats and trailing edge flaps make up what is known as the high lift flight system. Both slats and flaps extend outward from the wing in a curved downward motion, which dramatically alters wing shape to allow for a much steeper climb angle, while also mitigating the chances of a stall for takeoff and while climbing to cruising altitude. The curved slat supports ride on gears driven by a line of connected shafts back to the slat power drive unit. For the flaps, a flap carriage rolls outwards driven by its actuator arm as the supporting flap track beam lowers. A row of multifunction spoilers is situated at the wing's trailing edge to assist the ailerons with roll control. Special ground spoilers near the fuselage operate in sync for a lift dumping effect, creating downforce during landing to effectively stick the plane to the runway, slow the plane down, and put weight on the wheels for wheel braking. Along the wingtip and winglet, there are static dischargers, which are flexible metal rods that discharge built-up static electricity that builds from friction as the plane travels through the air. Landing gear. A strengthened portion of the wing has attachments for the main landing gear, which is tucked inside the wing and body during flight. A hydraulic retraction actuator is attached to the main landing gear strut in such a way to rotate the gear into position for landing. Bearing doors pivot with the rotating action. When the landing gear is fully deployed, a hinged side brace and locking stay with its own actuator keep landing gear locked firmly in place. These components unlock and fold with the landing gear for stowing. The nitrogen and oil-filled struts also act as shock absorbers during landing, with an attached hydraulic shimmy damper to reduce shimmy or shaking that occurs while under extreme landing forces. There's a heavy-duty carbon brake stack in each wheel. Rotors match with keys on the inside of the wheel so they rotate together. Stators are keyed to the axle and are stationary. During braking, electrically driven pistons compress the stack, and the resulting friction slows the plane down. The nose landing gear has slightly smaller tires and brakes than the main landing gear and operates in a similar way with the addition of a rack and pinion steering system. engines. Animagraphs already has an existing video about the inner workings of a jet engine. So for this video, we'll focus on the engine's relationship to airplane function overall. The rear of the engine case or cowling houses the thrust reverser assembly, which reverses fan thrust to slow the plane down just after touchdown, reducing wear to other landing parts and allowing shorter landing distances. The cowling exterior is a translating sleeve that moves backwards, pulling a ring of connected flaps into an angled position to block and reverse the normal path of thrust. Auxiliary Power Unit. The APU is a backup power source that can supply energy to things like cabin air conditioning, cockpit avionics, and so on when the plane is grounded and not yet connected to an airport power source. The APU also provides power to the main engines for starting. Pressurized air from the APU turns a small turbine device at the engine, which rotates the main gearbox and engine internals, starting the fuel and airflow process on which jet engines function. The APU itself is a gas generator that runs on principles similar to the core of a jet engine. The APU has an electric battery-powered starter. Air is drawn in through a port at the rear of the plane. It's mixed with fuel and ignited, and the resulting combustion drives a turbine to pressurize more air for various purposes, or run an electric generator. The APU exhausts out the back of the plane. Fuel. The center box and most of the internal wing area form a giant system of fuel tanks. The main containers are the left, center, and right fuel tanks. This plane can hold a maximum 5,681 gallons of fuel, weighing in at 38,350 pounds. The same ribs that provide wing structure become baffles with cutouts that let the fuel travel through the tank but also avoid excessive sloshing. Fuel enters through a port in one wing. A refuel-defuel panel in the wing-to-body fairing controls the fueling process and also shows fuel levels. Shutoff valves automatically open and close to ensure tanks are evenly filled. To greatly reduce fire risk, normal air in fuel tanks is replaced with nitrogen-rich air after refueling is complete. Bleed air valves on the main engines siphon off pressurized air, which is then cooled and passed through an air separation module to remove some of the oxygen, leaving a more nitrogen-rich product, which is then pumped into the fuel tanks. Surge tanks at the end of each wing act as vents for the main and center tanks, and have a NACA-style scoop that forces air into the tanks during flight, keeping positive pressure on the fuel system while allowing pressure changes depending on the elevation of the plane and the temperature of the fuel. These scoops also allow air to escape from the system during refueling. One-way flapper valves allow fuel to flow back into the main tanks, but not in reverse. The main fuel pump is located inside the jet engine casing, attached to a gearbox which is powered by the jet engine. Smaller collector tanks in each wing remain constantly full to provide uninterrupted fuel supply to the engine. To accomplish this, many supporting fuel pumps work to transfer fuel as necessary from the center and wing tanks. These pumps, called motive flow pumps, work by pressure alone, without moving mechanical parts, for simplicity and reliability. Fuel from the engine-mounted main pump flows through a nozzle into a narrowing tube, creating lower pressure in the chamber behind the nozzle, which sucks up fuel into the stream. Electrical boost pumps in each wing can act as a backup if other pumps fail. During normal operation, motive flow pumps transfer fuel from the center tank to main wing tanks, to collector tanks, and then to the engine. Air management. While in flight, pressurized air for crew and passenger spaces is collected from both the low and high pressure compressors inside the engine through bleed air valves. This hot bleed air is cooled with outside air through ram air ducts in the wing-to-body fairing before proceeding through the climate control system for further processing as needed. There's also a low-pressure ground connection for hooking up to an external air conditioning source while grounded. A network of air outlet tubes connects the system to cabin controls above each seat and in other areas of the plane. There are equalization valves between pressurized compartments to maintain equilibrium, and an outflow valve on the pressure bulkhead behind the forward cargo compartment. Hot bleed air is also used in the anti-ice and fog system. Perforated piccolo tubes in the wing slats use bleed air to melt ice. The air exhausts out the back of the slat. The front engine cowl is heated with hot bleed air and has small exhaust slots at the bottom. Windshields and side windows in the cockpit have a heating film between layers of glass. Electrical. There are 2 electrical equipment bays in the underside of the plane's body. The forward equipment bay is just behind the flight deck, and the mid-equipment bay is tucked behind the wings. These bays are filled with a dizzying array of electronics, computers, etc. to run the many systems on this complex airplane. Generators attached to each engine are the main source of electrical power. The APU can provide backup power. 3 separate electrical power centers control distribution to critical systems like landing gear, the high-lift flight system, brakes, tire pressure monitors, and many more. There are 2 primary flight control computers in the forward equipment bay, with backup alternate flight computers in the mid-equipment bay. Hydraulics. There are 3 separate hydraulic systems. Systems 1 and 2 are redundant in case one system fails. The third system operates only in emergencies. The base components for System 1 are nestled in the port side wing-to-body fairing. System 2 mirrors this arrangement, but on the starboard side. Hydraulic actuators, fitted in tight, small spaces, run many critical flight control surfaces. For example, the spoilers, elevators, rudder, and so on. There are often multiple actuators to operate a surface, connected to separate hydraulic systems, again for redundancy. Hydraulic System 1 controls the upper rudder actuator, left elevator outboard actuator, left thrust reverser, left and right multifunction spoilers 1 and 3, the flap power drive unit, left and right flap brake, left and right ground spoilers, and the landing gear. Hydraulic System 2 powers the middle rudder actuator, the right elevator outboard actuator, right thrust reverser, the right and left multifunction spoiler 4, the left aileron outboard actuators, nose wheel steering, the slat power drive unit, and the left and right slat brakes. Emergency System 3 can power the lower rudder actuator, left and right elevator inboard actuators, left and right multifunction spoiler number 2, left and right aileron inboard actuators, left and right slat and flap brakes, and the ram air turbine stow actuator. Water and waste. This plane has 3 bathrooms, one up front behind the flight deck, and 2 at the back. There are also sinks at the forward and rear galley stations. Pumps pull water from a 42-gallon tank anchored under the rear floor panels. A heated blanket and heated water lines keep the water from freezing. A water heater near each sink passes hot water through a water mixer to regulate faucet temperature. Gray water from the sinks is drained through heated gray water drain masts at the front and mid-rear of the plane's underside. Gray water drains in flight and evaporates in air. Black water from onboard toilets is stored in a waste tank and emptied after landing. Both air and water are separated from waste as it enters the tank. At altitudes below 16,000 feet, a vacuum generator creates suction to pull waste into the tank. Above 16,000 feet, the vacuum generator is bypassed, and the pressure difference inside and outside the plane creates the necessary suction forces. Emergency systems. The forward and aft galley stations have first aid kits, flashlights, fire extinguishers, crew life vests, megaphones, and portable oxygen cylinders that provide 15 minutes of oxygen to crew members. Oxygen generators are positioned above each row of seats. If the cabin loses pressurization, masks deploy, and a chemical reaction generates about 13 minutes of oxygen. An emergency locator transmitter automatically activates if a crash is detected. This transmitter emits a signal that can be used to help locate the aircraft. An aircraft identification module provides the location transmitter with aircraft-specific data. Door-mounted slides are packed into a bottom compartment in each passenger and service door. A lever in the door arms the slides so that it will deploy when the door is opened by attaching itself to the door sill and deflating. The overwing emergency exit doors are always armed, and an escape slide will deploy from a special compartment near the rear of the wing when the door is opened. In the event of full electrical power failure, a ram air turbine, or RAT, deploys automatically and works like a tiny windmill, using the plane's movement through the air to generate emergency electrical power. RAT power keeps emergency and landing gear systems active and provides power to emergency hydraulic system number 3. There are temperature-sensitive fire detection loops around each engine and the APU with spherical fire extinguishing bottles nearby. The equipment bays have smoke detectors, and cargo compartments have smoke detectors and fire extinguishing bottles. A flight data recorder monitors and records the last 50 hours of operational data and can hold 25 hours in its crash survivable memory unit. It has an underwater locator beacon that emits a signal for 90 days. An aircraft health management system stores maintenance data and monitors things like gust, turbulence, and hard landing conditions. Crew areas. There are front and rear galley areas with folding crew seats. The flight deck door is made of sturdy materials and has a bulletproof insert with a bullet-resistant peephole to the passenger cabin. The door latch prevents opening when pressure is applied from the passenger side. A keypad allows flight attendants to request entry into the flight deck. There's an override code for emergency access. Surveillance cameras monitor the area just outside the flight deck door. Stay tuned to the Animagraphs channel, as we'll be producing a companion video to this one covering the staggeringly detailed flight deck in full. External lighting and antennas. Navigation lights for aircraft visibility are installed in pairs in case a bulb burns out, with green lights on the right wingtip, red lights on the left, and white lights at the tail. Red flashing beacon lights and white strobe lights help aircraft avoid colliding with one another. There are flood lamps to illuminate the airplane logo and side lamps for wing inspections while on the ground. Lights on the left and right wing-to-body fairing and on the nose landing gear illuminate the runway during takeoff and landing. Taxi lights illuminate the area around the airplane while on the ground. The weather radar antenna performs multiple radar scans at different tilt angles. Antennas line the fuselage for things like radio communication to ground stations, collision avoidance and air traffic surveillance, GPS, a Ku band antenna for internet access, and more.